Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to talk about the general thermodynamic equations of state. Let's just jump right on in. Okay, I think I'll go ahead and stick with black today. Now, the equations of state for a gas, the PV equals nRT, the van der Waals equation, any number of other equations that you may or may not have seen, these are relations between pressure, volume, and temperature that have been derived empirically. We've run the experiments, we've derived these equations empirically. This is how gases sort of behave. Well, this is not sort of behave, this is how gases behave. Any other equations, maybe we took some equations and we modified them and derived different equations based on certain assumptions about atomic and molecular size or maybe attractive forces. So these are all empirically derived, the equations for the gas. Now, the equations of state for liquids and solids, well, it's pretty much the same thing. It's empirical observations and empirical derivations. So the equations of state for liquids and solids was expressed, or is expressed, I should say. Okay. Is expressed via experimentally determined coefficients. The coefficients of thermal expansion and compressibility. Thermal expansion and compressibility. Let me go ahead and write the equation. It is V equals V00 times 1 plus alpha times T minus T0 times 1 minus kappa times P minus 1, where V00 is the volume of the system, at 0 degrees Celsius and 1 atmosphere pressure. That's it. So this is the equation of state, just like PV equals nRT is the equation of state for an ideal gas. And the van der Waals equation is an equation of state for a van der Waals gas, a little bit more of a real gas, although not quite real behavior, but it's a little bit better than the ideal gas. This is the equation of state for liquids and solids. That's it. It just says that the volume at any given moment happens to equal this initial volume, which is the volume of the system at 0 degrees Celsius and 1 atmosphere pressure, times this. This is the initial temperature. This is the new temperature that you happen to be measuring. And this P is the pressure. So at a particular pressure, at a particular temperature, this is the volume. It's a relationship between pressure, temperature, and volume. And this is empirically derived, and it's based on these coefficients, the coefficient of thermal expansion and the coefficient of compressibility. That's it. Just another equation of state. So we have this equation of state for gases. We have this equation of state for liquids and solids. Is there a way to find one equation of state that applies all the way across the board? The most general equation of state that relates pressure, volume, temperature. The answer is yes. Okay. And, well, here's how we do it. So the equations of state. So these equations, let me just write a few more things here. These equations apply to systems at equilibrium. To systems at equilibrium. But we now have a more general condition for equilibrium. That's what we've done in the last few lessons. We've talked about this general condition of spontaneity, a general condition of equilibrium. For equilibrium, we have the following. Well, let me write this out, actually. But we now have a more general condition for equilibrium. And that condition is du is equal to TdS minus PdV, the fundamental equation of thermodynamics. This is the relation for a system at equilibrium. The change in its energy equals the TdS minus PdV. It's a relationship between energy, entropy, volume, pressure, temperature. This is the general condition of equilibrium. It's what we've been doing in the last couple of lessons. Okay, now, from this, let's see if we can actually derive a more general equation of state that applies to solids, liquids, gases, any phase, any system, any time, under any conditions. Okay, so let's see what we can do.